Hello, this is Dan Blake and Aaron Cook with our GIS project for CE 594R GIS Programming. Today is February 5th, 2014. For our project, we created an ArcGIS and Python program which generates optimal routes for a new railway service between Salt Lake City, Utah and Las Vegas. We started out with a good deal of data. Here on the map in ArcGIS, you see a green dot indicating Salt Lake City and a red dot being Las Vegas, with existing railways in black and existing major roads in brown. We incorporated a lot of data that we obtained from online, shape files and raster DEMs, and we used these to generate a least cost path analysis using ArcGIS's model builder and program that we developed. The first data set that we utilized here we're discussing is the DEM elevations. You see, this is our study boundary that we looked at, and so for each of these data sets we wanted to normalize them on a 1 to 10 scale so that we could use a raster calculator to determine them each with equal weights to determine the least cost path from Salt Lake to Las Vegas. So for the DEM, we simply divided the elevation here, you see on the left part of the screen, by 393.7, so that it would be on a scale of 1 to 10. Now here is another data set that we used, the presence of faults, geological faults, which is bad for earthquakes. So in each of these rasters we have it colorized so that red indicates less or least desirable and black is most desirable. So here you see a black area indicates that there are no geologic faults, and green has faults that are moving at a slow rate, yellow are faults that are moving at a faster rate per year, and red are more active faults. So in each of these rasters the least cost path analysis determines what's the best path according to these. Here's landslides. As you see, red are areas of high landslide susceptibility and yellow are areas of lower landslide susceptibility. This is the rivers raster. As you see, in all these red lines are the location of rivers. With a railway, we don't want to build on a river because that's expensive in constructing a bridge. Roads are represented here. Black are major highways, and for a railway line it's desirable to build near a road because right-of-ways already exist. So as just indicated, black here represents major highways, and yellow are smaller highways, and green are smaller highways, and red areas aren't as desirable to build on because there isn't any road. This raster displays railways. Black are more major railways that are already existent, and yellow are smaller or minor railways. So it's best to build along a previous railway. This is the slope raster, which we used geoprocessing capabilities in ArcGIS to calculate this based on DM elevation. Here you see black areas are indicative of valleys, and red areas are places with a very high slope. Now with railways, it's definitely best to avoid steep slope. That's a large factor in siting a railway line. This raster displays water bodies in our study boundary area. As you can see, here's the Great Salt Lake and there's Utah Lake. And yellow areas and green areas are places that might flood less often. Now for each of these raster sets we determined a common cell size of 500 meters or half a kilometer so that the raster calculations would all be very similar, and we could do that. Here is the model with the pre-processing for the data. You see we buffered a few of the shape files, we converted them to raster, and then we reclassified all of these rasters here in this line here so that they were on a scale of 1 to 10. Then using those reclassified rasters, we conducted a raster calculator which added each of these together, and then we used ArcGIS's least cost path analysis to generate the cost path from Salt Lake to Las Vegas. And we exported this model here to Python, which Aaron will now describe.
Thanks, Dan. So as Dan said, we exported this model into Python, and we created a Python script which could be run and edited by the user so that we could have a very nice and simple run each time. Because each of the 1 to 10 raster files are used every single time, we figured it would be best to just create them once, be done with it, and then call them into this program to be used now that they're all created. Since we talked about the methodology, we would multiply the 1 to 10 scales by different weight factors. The first thing that the user is able to modify is a list for each of the factors included in the analysis. So for the first one, it weights the elevation with a factor of 4 and everything else with a factor of 1. At the bottom we have the multiplier descriptor, and so in this one it's elevation because elevation is the most important factor. We go through a weight with having one factor being the most important throughout all of them, just to get a baseline, see what each one of them considered almost on its own would produce. And then we do an equal weight one in the middle where you can see that everything has a weight of 1 or equally weighted. And then we do more complex analyses where, for example, we want to avoid moving land, so higher elevation where snow slides out, or avalanches, or faults, or landslides, or high slopes should all be avoided, and so they get a much higher cost factor. We go through several different types of analyses with these, ending with both a guess by myself, which weight all of these differently based on how I think that a real railroad would be affected by that, and then Dan's guess by how much each of these would be weighted. So then we set the working folder to all roads lead to Vegas and import everything that we need in order to run the script, both from ArcPy and OS, and then we let it overwrite things and import the spatial analyst, as well as check out the extension for it. We set the current map document to be the MXD template, so then that way it knows how to create the PDF when we come to that point. We check if the path exists, and then call up the PDF doc. We set all the local variables here, so we set the point for Salt Lake City and Las Vegas. Then we call all the clipped DEMs and the 1 to 10 faults files all as rasters. These are all intermediate files, the cost raster, the cost distance, backlink, and cost path. But then the cost path add is the output file that we have at the end of the process. So then we have for I in range from 0 to the length of whatever the length of this DM multiplier list is. So this is how the user can add or remove entries from this list without having to go down in the actual code and change how many iterations this runs. When we set this cost raster value, it'll come out as a raster because everything into it is a raster. So we tell Python that we're dealing with a raster from the DEM clip variable, and then we multiply it by the DEM multiplier. Now, Dan said that we divided by 393.713 to make it on a 1 to 10 scale. This is where it actually happens. then everything else is already on 1 to 10 scale, so it is multiplied by its entry in the list. So on the ith entry, it'll call the faults, and I'll call the landslides multiplier and the rivers raster, and so on and so forth until we have a complete raster with the cost for each cell. It prints the string that, or the multiplier descriptor that we're on at that moment, so that we don't go crazy and we know it's actually running. Then it runs the cost distance analysis. So I'll find the cost for each cell from Salt Lake City, and then using that information with the cost distance shape 1, it will find the least cost path to Las Vegas and output a raster with that path. Then we use the raster to polyline to convert that cost path shape to our cost path add output file. We call it cost path add because we were considering doing a more multiplicative cost path analysis, but we figured that addition would be a lot easier since multiplication is distributive, and so we couldn't really multiply each factor individually. This is just for user readableness at the end document, so then it will redefine the element names in each of the files. So here in the layout we have elevations, and then it's named this one, it's named elevation box, so it's updating these fields dynamically, as well as this name field for what one that is. When you run it, we just have to load it into the Python module as normal. It does not stand alone. And then it will update all of these to the multiplier that they're individually considered, as well as doing the multiplier descriptor at the top. It will create a PDF with the multiplier descriptor, and then it'll export that to a PDF using the template we defined already, and then it will append that page to the PDF doc we started at the very start of the code. At the very end, it will save and close the PDF doc, and then we end up with our finished product, which is a proposed railway route from Salt Lake City to Vegas based on elevation, faults, landslides, rivers, road, railways, slope, water, equal weight, moving land, washout, earthquakes and wetlands, extant right-of-way, slope and snow, low railways, slip slide and way, or high landslide, or moving earth potential, my guess as well as Dan's guess. So this is our project. We hope you enjoyed, and have a great GIS experience.